Evidence from the field of astrobiology implies that life in its most basic form can be found virtually everywhere in the universe. It has most likely occurred several times in our own solar system. However, proving the presence of human-like, technologically advanced life forms is a much more difficult prospect. It all comes down to solar energy. The first simple life on Earth probably began underwater and in the absence of oxygen and light, conditions that are not that difficult to achieve. Humans have long speculated what life may be like on distant planets, and this question can now be answered owing to the James Webb Space Telescope, the most powerful telescope in existence. The first clear evidence of carbon dioxide in the atmosphere of a planet outside the solar system has recently been discovered by NASA's James Webb Space Telescope. This observation of a gas giant planet 700 light-years away, in the orbit of a sun-like star, provides critical information on the planet's composition and evolution. After this discovery, NASA Administrator Bill Nelson promised that humanity will soon have a wholly unique view of the universe, unlike anything we've ever seen before. So today, we'll look at the latest James Webb Space Telescope discoveries and analyze what it means and what else is out there. The James Webb is outfitted with 2 infrared cameras. The first is a near-infrared camera, often known as an NCAM, which records shorter infrared wavelengths. The second device is a mid-infrared camera, commonly known as a MIRI-cam, which records longer infrared wavelengths. The images exhibit a variety of unique characteristics based on the camera that was used to capture them. So far, NASA has released a slew of images captured by this gigantic, one-of-a-kind telescope, and they are, to put it frankly, amazing. Stars emitting spectacular blue and orange light, galaxies whirling and crawling around one another in a tangle of stars and dust clouds, and some of the universe's oldest light, emitted 13 billion years ago, have all been observed. So far, the data collected looks to be safe, but you never know when things will change. After all, NASA anticipates that this telescope will be able to view light from the universe's farthest reaches, which might be as dangerous as it is exciting. Recent NASA findings have academics and researchers all over the world delighted. Last month, an international team of astronomers using NASA's James Webb Space Telescope collected an in-depth inventory of the deepest, coldest ices yet observed in a molecular cloud. The team was able to identify frozen versions of a wide spectrum of molecules, from carbonyl sulfide, ammonia, and methane, to the simplest complex organic molecule, methanol. In addition to simple ices like water, this is the most complete census of the ice components available to make future generations of stars and planets before they are heated during the birth of newborn stars. This image from the telescope's near-infrared camera shows the central part of the chameleon dark molecular cloud, which is located 630 light-years away. The brilliance of the young outflowing protostar, IRAS 110 IRS-4, illuminates the chilly, wispy cloud material in the infrared. The light from several background stars visible as orange dots behind the cloud can be used to detect ices in the cloud, which absorb starlight as it passes through them. This study was part of Webb's Ice Age project, one of 13 early release science programs. These observations are intended to demonstrate Webb's observing capabilities and teach the astronomical community how to get the most out of its instruments. The Ice Age team has already planned additional observations with the goal of tracing the evolution of ices from their formation through the production of icy comets. Just 1 week before this discovery, JWST imaged the inner workings of a dusty disk surrounding a nearby red dwarf star. These observations represent the first time the previously known disk has been imaged at these infrared wavelengths of light. They also provide information about the disk's composition. The star system in question, AU Microscopium, AU MIC, is 32 light-years away in the southern constellation Microscopium. It's about 23 million years old, which means that planet formation has ceased, as that process usually takes less than 10 million years. The star has 2 known planets discovered by other telescopes. The dusty debris disk that remains is the result of collisions between remaining planetesimals, a more massive analog of the dust in our solar system that causes a phenomenon known as zodiacal light. AU MIC was studied using Webb's NCAM, and scientists were able to analyze the region very close to the star using CAM's coronagraph, which blocks the bright light of the core star. The NCAM images allowed the researchers to trace the disk as near to the star as 5 astronomical units, 460 million miles, the equivalent of Jupiter's orbit in our solar system. The observation program captured images at wavelengths of 3.56 and 4.44 microns. The scientists discovered that the disk was brighter at shorter wavelengths, or bluer, implying that it includes a lot of tiny dust that is better at scattering shorter wavelengths of light. This discovery is consistent with previous research, which revealed that the radiation pressure from AU-Mike, unlike that of more massive stars, is insufficient to eject fine dust from the disk. While identifying the disk is crucial, the team's ultimate goal is to hunt for massive planets in broad orbits, such as Jupiter, Saturn, or our solar system's ice giants. These worlds are extremely difficult to discover in the vicinity of distant stars using either the transit or radial velocity approaches. In another discovery, an asteroid roughly the size of Rome's Colosseum, between 300 to 650 feet, 100 to 200 meters, in length, has been detected by an international team of European astronomers using Webb. Their effort made use of data from the calibration of the mid-infrared instrument MIRI, during which the team discovered an interloping asteroid by chance. The object is likely Webb's tiniest to date and could be an example of an object measuring less than 0.6 miles, 1 kilometer, in length within the main asteroid belt, which is located between Mars and Jupiter. More observations are required to better characterize the nature and features of this object. These Webb observations, which were published in the journal Astronomy and Astrophysics, were not intended to search for new asteroids. Rather, they were calibration photographs of the main belt asteroid 10920 1998 BC1, which was found in 1998. The observations were carried out to evaluate the performance of certain of MIRI's filters. However, the calibration team determined that they failed due to technical issues, such as the brightness of the object and an offset telescope pointing. Despite this, the scientists used the data from asteroid 10920 to develop and test a new technique for constraining an object's orbit and estimating its size. The method's validity was established for asteroid 10920 by combining MIRI observations with data from ground-based telescopes and the ESA's Gaia mission. During the MIRI data analysis, the team discovered the smaller interloper in the same field of view. According to the team's findings, the object is 100 to 200 meters in size, has a very low inclination orbit, and was located in the inner main belt region at the time of the Webb observations. The discovery of this asteroid, which the team believes is the smallest observed by Webb to date and one of the smallest detected in the main belt, would have significant implications for our understanding of the formation and evolution of the solar system. If confirmed as a new asteroid discovery, current models predict the occurrence of asteroids down to very small sizes. However, due to the difficulty of observing these objects, small asteroids have been studied in less detail than their larger counterparts. Astronomers will be able to study asteroids smaller than 1 kilometer in size in the future, thanks to dedicated Webb observations. Furthermore, this finding suggests that Webb may be able to contribute to the discovery of new asteroids by chance. The team suspects that even short MIRI observations close to the solar system's plane will always include a few asteroids, the majority of which will be unknown. With all of the discoveries the JWST is making every day, it is reasonable to wonder, will it find life on any other planet or exoplanet? Since the dawn of civilization, humans have speculated about whether or not there is life elsewhere in the universe. There were no known planets outside of our solar system 20 years ago, but since then, over 4,000 additional planets, also known as exoplanets, have been discovered orbiting other stars. According to NASA, the cosmos could be home to trillions of exoplanets. Extraterrestrial plant life may include the earliest traces of life beyond our solar system. When the Galileo spacecraft was on its way to Jupiter, it turned its instruments back towards Earth and discovered a clear sign of the presence of plants. The vegetation red edge, VRE, biosignature was discovered by the sensor as a combination of red and infrared lights reflected by plants. For example, a planet covered with rainforests such as Earth should have a strong and easy-to-detect VRE signal. The JWST will measure the VRE of distant, Earth-like planets in the habitable zone near stars. These might be significant life signs in the exoplanet atmosphere. When sunlight passes through the star of a planet, the JWST may be able to detect it when it enters its atmosphere. The missing wavelengths of light would subsequently be detected via spectroscopy. Atoms and molecules in the atmosphere absorb specific wavelengths, creating a unique fingerprint that the JWST can detect. This method can be used to determine the makeup of the atmosphere and whether or not life exists. Life is expected to exist on Earth-sized planets with atmospheres similar to ours. Proxima Centauri, a red dwarf star 4.25 light-years from the Sun and our nearest star, provides the best opportunity for humanity to observe city lights. On another planet, as it stands, Proxima Centauri b, a rocky exoplanet orbiting this star, is one of the most Earth-like planets scientists have discovered. With the Webb telescope's incredible capabilities, it may soon provide us with unprecedented views of distant planets and exoplanets, allowing us to answer the age-old question: is there life elsewhere in the universe? The James Webb Space Telescope, JWST, has already transformed our understanding of the cosmos, and its continued discoveries promise to reveal even more about the universe's formation and the potential for life elsewhere. As the most powerful space observatory ever built, JWST has a unique advantage in its ability to observe distant objects and phenomena in unprecedented detail, particularly through infrared wavelengths. This capability allows it to peer through cosmic dust clouds, observe distant galaxies, and even capture the faintest signals from exoplanets located light-years away. One of the most exciting aspects of JWST's mission is its ability to study the atmospheres of exoplanets with greater precision. While astronomers have long speculated about the potential for life on planets orbiting distant stars, the ability to analyze the chemical composition of their atmospheres will provide definitive clues about their habitability. For instance, the detection of certain gases, such as oxygen, methane, and carbon dioxide, could suggest that a planet is capable of supporting life in a way similar to Earth. This type of atmospheric analysis could be the key to finding Earth-like planets that harbor microbial life or even more advanced organisms. Beyond just the search for life, JWST is also poised to answer some of the most fundamental questions about the universe's origins. The telescope's advanced technology allows it to capture images of galaxies and star-forming regions that are billions of light-years away, providing a glimpse into the universe's past. By studying the light emitted by these distant objects, scientists can learn more about the processes that led to the formation of stars, galaxies, and planetary systems. These insights could offer valuable clues about the early universe and how the conditions that support life came to be. JWST is also shedding light on the birth and evolution of stars. One of its key projects involves investigating star-forming regions, where dust clouds collapse to form new stars. The telescope's infrared capabilities allow it to peer through the thick dust and gas that surrounds these regions, revealing the processes that are usually hidden from view. These observations are critical for understanding the life cycle of stars, from their formation to their eventual death, and how these stellar processes impact the surrounding environment. Moreover, the telescope is contributing to the study of dark matter and dark energy, two of the most mysterious components of the universe. While JWST is not specifically designed to detect these invisible forces, its observations of galaxies and the structure of the universe can provide indirect evidence of their existence and properties. By mapping the distribution of galaxies and observing their behavior, scientists can infer the effects of dark matter and dark energy, which are believed to make up the majority of the universe's mass and energy. As the JWST continues its mission, it is set to revolutionize our understanding of the cosmos in ways we cannot yet fully predict. With its unmatched ability to observe the universe in infrared, the telescope is providing a new perspective on some of the most fundamental questions of astronomy, from the origins of galaxies to the potential for life beyond Earth. Each discovery brings us closer to answering the ultimate question: are we alone in the universe? As the James Webb Space Telescope, JWST, continues to explore the farthest reaches of the universe, its capabilities are enabling scientists to delve into previously uncharted territories of cosmic discovery. One of the most significant areas where JWST is making an impact is the study of exoplanet atmospheres, particularly in the search for biosignatures. By capturing detailed spectra of light passing through the atmospheres of distant planets, The telescope can identify specific chemicals that may indicate the presence of life, such as oxygen, methane, or even more complex organic compounds. This could revolutionize our understanding of whether Earth-like conditions are common across the universe and whether life beyond our planet is a realistic possibility. The potential for JWST to identify habitable exoplanets also extends to the search for planets that could harbor life in environments radically different from Earth. For example, some planets may have dense atmospheres of gases like sulfur dioxide or hydrogen sulfide, which, while toxic to humans, could support entirely different biological processes. JWST's ability to analyze a wide variety of atmospheric compositions may help us rethink the types of environments where life could exist. Such discoveries would open new avenues of exploration and challenge our assumptions about what constitutes a habitable world. In addition to its exoplanetary research, JWST is shedding light on the structure and evolution of the universe itself. By observing distant galaxies and star systems, the telescope is providing a more comprehensive understanding of the distribution of galaxies across vast cosmic distances. This information is essential for understanding the large-scale structure of the universe and how galaxies form and evolve over time. Furthermore, these observations help refine our models of cosmic inflation, dark matter, and dark energy, concepts that are central to our understanding of the universe's origins and fate. As JWST continues to operate, its groundbreaking discoveries will likely challenge our existing theories and inspire new ones, driving humanity's understanding of the universe forward. The ongoing mission promises to be a new era of discovery, one that may not only answer questions about the cosmos, but also pose entirely new ones.